This is Multivariable Calculus, Chapter 12, Vectors and the Geometry of Space, Section 12.1, Three-Dimensional Coordinate Systems. We know from geometry that to locate a point in a plane, two numbers are necessary. We know that any point in the plane can be represented as an ordered pair of real numbers, where one is the x-coordinate and the other is the y-coordinate. And for this reason, we call a plane to be two-dimensional. To locate a point in space, we need three numbers. We can represent any point in space as an ordered triple of A, B, and C of real numbers. In order to represent the point in space, we need to first choose a fixed point, the origin, and then three directed lines through the origin that are perpendicular to each other, called the coordinate axes, and we label them the x-axis, the y-axis, and the z-axis. Typically, we think of the x and the y-axes as being horizontal and the z-axis as being vertical, and we draw the orientation of the axes as shown in Figure 1. The direction of the z-axis is determined by the right-hand rule, as illustrated in Figure 2. So if you curl the fingers of your right hand around the z-axis in the direction of a 90-degree counterclockwise rotation from the positive x-axis to the positive y-axis, then your thumb will point in the positive direction of the z-axis. The three coordinate axes will determine then the three coordinate planes as shown in Figure 3. The xy plane is the plane that contains the x and y axes. The yz plane contains the y and z axes, and the xz plane contains the x and z axes. These three coordinate planes divide space into 8 parts called octants. The first octant in the foreground is determined by the positive axes. Now, if P is any point in space, we let A be the directed distance from the yz plane to P. B is then the directed distance from the xz plane to P, and C is the directed distance from the xy plane to P. We can represent then P by the ordered triple A, B, C of real numbers, and we call A, B, and C the coordinates of P, as in A is the x-coordinate, B is the y-coordinate, and C is the z-coordinate. Thus, to locate a point, A, B, and C, we start at the origin and move A units along the x-axis, and then B units along the parallel to the y-axis, and then C units parallel to the z-axis, as shown in Figure 4. The point then determines a rectangular box, as shown in Figure 5. If we drop a perpendicular from P to the xy plane, we get a point Q, as shown here, with coordinates A, B, 0, which is then called the projection of P onto the xy plane. So Q is the projection of P onto the xy plane. Similarly, R is the projection of P onto the yz plane, and S is the projection of P onto the xz plane. We call the Cartesian product R cross R cross R, which is all x, y, and z, such that x, y, and z are contained in the real numbers, are the set of all ordered triples of real numbers, and we denote this by R cubed. In two-dimensional analytic geometry, we consider the graph of an equation involving x and y is a curve in R squared, or 2 space. In three-dimensional analytic geometry, an equation involving x, y, and z is a surface in R3, or 3 space. And we can see then that the equation y equals 5, instead of representing just simply a line in the xy plane, represents a plane in the three-dimensional coordinate system. Similarly, the plane z equals 3 is a plane that is then parallel to the x and xy plane and intersects the z-axis when z equals 3. So the familiar formula for the distance between 2 points in a plane is, we know from geometry, and the distance is given by the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And we can then extend this to 3 dimensions very easily by adding in then the difference of the z-coordinates quantity squared. And this gives rise quickly to the definition of a sphere. A sphere is defined as the set of all points P, x, y, and z, whose distance from C, or the center, h, k, and L is r. So beginning with the distance, so we know that the magnitude of PC is r, which is the square root of x minus h quantity squared plus y minus k quantity squared plus z minus L quantity squared. If we then square both sides, we end up with r squared is equal to x minus h squared plus y minus k squared plus z minus L squared, which we should recognize as the equation of a sphere.